Hello Reginasailing family and friends. We are sailing, we assume we are sailing from Malta in direction west-northwest along the south coast of Sicily, but we can't see the Sicily, but we can see the moon. So we will try to shoot the moon. The moon, you will soon recognize, is not the perfect object to shoot because the moon is moving so fast and you have to do so many corrections. It has a huge parallax, it's very close to us, so you have to do a lot of more calculations and be very precise with the time. But let's try it because it's fun. It's fun to see if we can use the moon. So for that reason I have made a template for the moon, and it looks pretty much the same as for planets and the sun, but it does have some differences further to the fact that I have marked it with the moon up here. It is that you have, when you calculate your corrections for your true altitude, you have here a first correction and a second correction to take into consideration. And then you have an upper limb correction which you might be doing, and that is what we're going to do today, because if we have the horizon there, we chose to shoot the upper limb today. So we placed the moon under the horizon, and the reason for that is that we had the crest like this, so it was very nice and easy to put the moon on the upper limb under the horizon. The alternative would have been to put the moon on top of the horizon, but if the crest looks like this, it is not so easy to determine if that little point is exactly on the horizon or not, never mind the fact that we are missing some part of the moon here. So we have measured the upper limb. And we are, as we said, today on the 29th, I haven't said it, but I'll tell you now, we are on the 29th of March, and we have an approximate position. We have 36 degrees and 40 minutes. That's where we think that we are on the northern hemisphere. Obviously, we think we are by dead reckoning that we have come 13 degrees and 09 minutes east. So we are on easterly longitude, which makes it a bit more fun and more calculations. The time of the shooting was, and you always try to note the seconds first because they change the fastest, so you keep forgetting what were the seconds. Then the minutes are not that fast, so this is how you note it on deck, 48 minutes, and in the very end you add the hours because they don't change until very much later. We have a longitude and a course over ground. We don't need to take these into consideration now because we're not going to do a transferred position line because we see the sun and the moon at the same time, so we're going to get a fix immediately. So now let's see what was the altitude that we shot the moon, and we shot the moon at an altitude of 57 degrees and 2 minutes. That's what we did. So now we do all these corrections. Some of them are you are familiar on. So index error, my sextant has 4 minutes on the arc, let's say. If it's on the arc, we have to take it off again, so we deduct 4 minutes. So we get down to 56 degrees and 58 minutes. Then we have a dip. Well, on my boat it's 2.8 meters above the water level. That has to do with the eye height. We look at the dip, and as you can remember, 2.8 is about 3 minutes we have to deduct there. It's easily remembered because it's always the same if you have the same height of the eye. Of course, if you are sitting down or standing up, it makes a little difference. The apparent altitude is thus 55 minutes here, 56 degrees and 55 minutes. Now it becomes a bit interesting. You have a first correction and a second correction. And the second correction, for that you need the HP factor. That's the horizontal parallax factor of the moon, because it has such a huge parallax. So how big is the parallax today? this is written in a blue box. It's written in the second column because you find it on the daily pages of the Nautical Almanac. So we will first have to find the HP factor, and then we can do the second correction. The first correction has nothing to do with the HP factor, but let's look up the HP factor here first. So the 29th of March is somewhere on this page. 29th of March. Moon is the second column. We have first sun and then moon. And then let's go down here. At 12 o'clock, there we have a lot of information, Greenwich hour, angles and so on, declination. But back here, 55.1, that is the HP factor, the horizontal parallax. So at 12 o'clock we have 55.8. We shot at 12:48, so it's closer to 1 o'clock. So we look down here, but it's nevertheless 55.8. So the parallax is the same if we have shot it at 12 o'clock or 1 o'clock. All right, 55.1. So we write this down here, 55.1. We need that for the second correction. Now let's see how we find the corrections at all. These are in the very back of this book, my book. And it's in the back because people don't need it so much, I think. Here it says the correction table for the moon, 0 to 35 degrees on the sextant and 35 to 90 degrees on the sextant. You will most probably not really remember how you do this after a year. And therefore, I have made a template or some footnotes. So I mark down here how you do with the moon. I've written here in short steps, and hopefully you will remember how you go down the way to find all the corrections. So this is for you to remember how you do this. I will show it to you on the real page now from the almanac. So we have to find our apparent altitude. Well, the apparent altitude is 56 degrees, 55 minutes. Here 56 degrees. Yes, 56 degrees is in this column. 56 degrees. And how many minutes? Well, my memory isn't that good. 56 and 55. So we go down. So there is 50. So that's the correction. So for 56 degrees and 50 minutes, the correction is 41.6. For the next full degree, it would be 41.4. We have 55 minutes, so it's in between here. So if you want to be really precise, you could say it is 41.5. So let's call it 41.5. So that's 41.5 as the first correction. Now the second correction, you now know that you are in this column, because we have measured 56 here. So what you do is that you go down, you stay in the same column, and then you come to an intersection. You have to decide if you have a lower or upper limb. So in our case, we use the upper limb. And then we have to find the HP factor here to the left. So we go down, and the HP factor was 55.1. So 55.1 is approximately 55.2. So we use the upper limb. So you can see that we should have the second correction of 2.9 minutes. 2.9 minutes in that column. 2.9. 2.9. All these we add together. So 9 plus 5 is 14. And that's 5, 8, 9. And that makes 5 plus 4. Well, it is 60 minutes to a degree. So that means it makes 30 here and gives a full degree there. So that is then 57 degrees and 39 minutes. Now, since we shot the upper limb, we have to deduct 30 minutes from that. So 57 degrees and 39.4 minutes minus 30 minutes is 5709.4 minutes. That is our true altitude. Well, isn't that nice? So now we have seen that it's not much different, rather except for the fact that you have to have a first correction and a second correction. Now let's go over and determine the position of the body, of the moon in this case. So here it looks very similar as well, despite the fact that we have a D factor and a V factor to take into consideration. The D factor is because the declination is moving so fast, so you have to take that into consideration from hour to hour. And the V factor is that it differs, the increments differ depending on what time of the day or which day it is. So let's go through this step by step. We choose the working latitude. So we have 36 degrees and 40 minutes north. So our working latitude, the closest full degree of a working latitude, would be 37 degrees north. And now the declination at full hour. Okay, the declination, that is found on the daily pages of the 29th of March. The 29th of March is here. We have the declination there. So we have to go down all the way to the 29th and then at 12 o'clock. So you can see that at 12 o'clock the declination is 18 degrees and 53.1 minutes. Looking at what the declination is at 13 o'clock, you see this is a considerable difference. It is 19 degrees and 0.7 minutes north. So first of all, we have to note that it has increased from 12 to 13. So if we take the full hour at 12 o'clock, the 18 degrees 53, we then have to add something. So the D factor is positive. D factor is the difference. The difference between those two is 7.6. So that's the column, if you look up here, of the D factor. So the difference is 7.6. How for the full hour? So, but we are not going a full hour from 12 to 13. We are going 48 minutes. So we have to note how much 48 minutes means in respect of that it changes 7.6 minutes. There are two ways of doing this. 48 minutes, that's 48 60th. So we want to take 48 60th of 7.6 and add it to that. Or you look at the increments page. We write this here, 7.6. And then we look at here the 48 minutes. 48 minutes. And never mind the seconds, we don't need to take that into consideration. So this here is valid, the V or D factor is valid for the whole 48 minutes. So we look at our D factor, which was 7.6. Where is 7.6? It's back here. So 7.6 for the weight of 7.6 in 48 minutes is 6.1. So for a full hour, we would have to add 7.6 minutes, but for the 48 minutes, we only add 6.1, which is the same as 48 60th of 7.6. 6.1 minutes, that's what we write down here. 6.1, and then of course the declination full hour, we never note it down, and I have already forgotten. 29th of March, what was the declination for the moon? It was 18 degrees and 53.1 minutes. 1853.1. So the declination is 1853.1 at full hour, and these 48 minutes make that it added another 6.1 minutes. It can be negative, as I said, if the declination decreases from hour to hours. Keep an eye on the fact if the declination has increased or decreased in the coming hour. In this case, we add it. So the total declination is 0.29518. So the declination is 18 degrees 59.2 minutes. Now how about the Greenwich hour angle? The same thing here. We first take the Greenwich hour angle at full hours, then we add the normal increments, and then we see what the V-factor tells us. So we look at the Greenwich hour angle of the moon for the 29th of March, there. We go down to the 29th of March, and we see that the Greenwich hour angle is 303 degrees 34.6 with a V-factor, if you go up there, V-factor, with a V-factor of 12.2, which you had to add for a full hour, but we only have 48 of these minutes. So for a full hour we should have added another 12.2 minutes. So what we do is that we write down the Greenwich hour angle at full hour, 303 degrees and 34.6 minutes, and then we note the 12.2 as the V-factor. So here is the Greenwich hour angle. So we write here 303 degrees and 34.6 minutes. And the V-factor here we said was 12.2. That's just a factor. And then we will see how many minutes this becomes depending on the 48 minutes. Now we have the increment, the just normal increment for 48 minutes and 24 seconds. So we have to be very accurate because the Greenwich hour angle changes so fast. We have 48 minutes and 24 seconds down here. Now don't go in the wrong column. You have sun and planets, areas and moon. So it's the third column there, which you have to go down. So if we look here at 28 minutes and 24 seconds, we have an increment of 11 degrees 32.9. So that is 11 degrees 32.9. And then we have the V-factor. Again, we look at the same page for 48 minutes. So if we have a V-factor, here you can look V or D factor. V-factor of 12.2. V-factor of 12.2. How much weight does that give for 48 minutes? So 12.2 is here. So 12.2, which would be valid for a full hour, in 48 minutes, we only take 9.9 of these 12.2 into consideration. So 9.9 we have to add. 9.9. Now the V-factor for the moon is always positive. That's why you always have a plus here, like the increments, always positive. On my template for the planets, the V-factor could also be negative, but that's easily found. So if you look at here, for instance, in February, regarding the Venus, you go all the way down at Venus, you see that the V-factor says minus 0.1. So it clearly says that it has a negative sign. So you can't do much wrong when you use the V-factor for the planets. But for the moon, it's always positive, which makes it a bit easier. So now what we do here, and we add all these together. So this becomes 424. This is then 17. 3 plus 3 is 6. That means a full degree. Plus 1 is a 1 down here. The full degree I note here. So 303 plus 11 plus 1 makes 315. So that's the Greenwich hour angle of the moon at exactly that time. Now we want to choose a longitude. Now the longitude, in my case, is that I have easter longitude. And easter longitude means that you have to add these two figures together. You add these two figures together, so it becomes 0, 0, 0. So that's be a little bit, because there it is a plus, because we have easterly longitude. Now, what shall we write here so it becomes 0 for adding? If we write here 6, that would work, wouldn't it? 4 plus 6 makes 10. So we put this here. So what should we write here? Well, if we write here a big 2, you would see that if you add them together, 7, 8, 9, 10, that becomes a 0 as well. So that's good. But that becomes a 10, so we have to have 1 there. And now the question is, what do we write here in order that it becomes 0 there? So if we add and then you have to consider that it's 60 minutes to full degree. So look here, if I write a 4 there, we have 1 plus 4 is 5, plus this one from that decimal over here makes 6. So that's a full degree. So I can write 0 here, it's meant to be here over here, full degree. So we mustn't forget this one when we calculate the local hour angle. That's why Western latitudes are a little bit more easy, because you just copy the figures from up here down there. Now, we have 13 degrees and 9 minutes. We want to write here something which has 42 in the end, which is as close as possible to this position. So, if I write 13 here, 1342, that's quite far from 1309. There is another position which is closer, because if I write here 12 degrees, 42.6 minutes, then this is pretty close to 13 degrees and 9 minutes, because you would only need 17 minutes to get to 13, and then another 9 to get 13 degrees and 9 minutes. So 12 degrees and 42.6 minutes is the closest you can get to 13 degrees and 9 minutes. Now let's add this together now. We have done this here, 6 plus 6 is 10, I'll write it down here, da. Now 5, 6, 7, 8. So here comes an 8, and this becomes 2, and this becomes 3, 328. Now if you didn't quite get it why I chose 12 degrees here instead of 13 degrees there, just think of it. Switch off the video and just think of it, which number you should place here, which full degree, so this longitude becomes as close as possible as this longitude, and it shouldn't be more than 30 minutes apart, because if it is more than 30 minutes apart, you should take the next degree. So we have now chosen a longitude of 12 degrees of 42.6 minutes to get this local hour angle. So we have already 2 things that we can note down here: the working latitude, which is 37 degrees, and the chosen longitude, which is 12 degrees and 40, call it 3 minutes east. Done with second column. Now comes the third column. Let's find the page in the sight reduction table for the working latitude, which is 37. Same or contrary. Well, the declination of the moon, which we saw was actually northerly. I forgot to write this down. Do you want to see that again? Well, I can show you. If you don't believe me, I'll show you on the book. Here, 29. It's always good to have a second check. And you go down there and you see that it says north 1853 and 1902. So it's northern declination. So they're both north. So that means that we are on the same hemisphere. And the declination range, 1853, is here. So that means that I have now looked up I have my sight reduction table in the boat, unfortunately, so I had to print it out here. Don't print it out, there are hundreds of pages. So just if you want to do an exercise, you can print it out. It's much better to buy the book. But for exercises, this is good enough. So what do we look up here? We choose the declination. First we can check, it's always good to do the checking. We have latitude 37 degrees, we have same there, and we have the correct range, So that's good. Now we look up the column of degrees of declination. So the degrees of declination is 18. You can see here, 18. It's pretty close to 19, you can see that. But let's do, no, that's not 18. Here it says 18. It's pretty close to 19, that's true. But it's the full degree is 18. And these 59 we'll take care of later, because these 59 minutes we will see how heavy they weigh, and we will use them here as a correction in the top right corner. So right now we look at 18 degrees. We look at the row of local hour angle. Well, we chose the local hour angle of 328. So we go here, 328. It's in the middle center row there. So it's in the center there, and we have the column here. So here, and that is pretty difficult to do on a rocking boat. So you will prove it. 18 degrees, and we have these figures. It is 56 degrees and 7 minutes on the Sextant HC. The weight, the D factor, is 36, and the Z is 115. So I'll write these down here. 56 degrees and 7 minutes. The D factor is 38. 38. It's a plus. It can be negative as well, but that's only if you are on the contrary. So if it's on the same, it's plus, and the Z was 115. Now let's take now these 59 minutes into consideration, because the declination is not 18 degrees, it's 1859 minutes. So these 1859 minutes we have to take into consideration there. How much will they change depending on this D factor? So we go into table number 5. First we copy this 56 degrees and 07 there, and then we go into table 5. Table 5 is here. Well, it's in the back of the sight reduction table normally. So now we look at the D. The D is 38. The D is 38. So this is the column we shall look for. And then we have 59 minutes. Well, 59 minutes is all the way down here. 59 minutes. That's almost the full weight. So we go down there. So it's actually 37. So 38 it would have been for a full degree. So it is, since we're almost in a full degree, we're almost in 38. So that's 37. And if you want to see it, you can see down there it says 37, because we are at 59 minutes and the D factor up there of 38. All the other marks were from the previous exercises we have done. So I only printed one table 5, as you noticed. So we add these two. 7 plus 7 is 14, and 3 plus 1 is 4, and here it says 56. Now this is what we have, what we should measure, 56 degrees and 44 minutes. What we did measure is 57 degrees and 09.4 minutes. So these two have to be compared. Well, first of all, we can say which one is larger. Well, obviously this is larger. We measured something larger than we should. So if this is a bigger number that we have measured, we must be closer to the body. So we are closer to the body because the angle is bigger. Now we write the larger figure up here, so we can then deduct them from each other. 56 degrees 44 minutes. So we see what the intercept is, the difference between these two angles. So from 4 to 9 is 5, and from 4, be careful, because it's only 2 to full degree here, because it's 60 minutes to a degree. So we put that here. So it's 25, and that is 0. So it's 25 minutes, which means 25 nautical miles. That's red. We write this down here, 25 nautical miles. Now what's the azimuth? Oh yes, azimuth. Azimuth is maybe the Z, depending on the local hour angle. So if the local hour angle is larger than 180 degrees, well it is, that is Zn, the azimuth is the Z. So it's 115, so it's 115. So now we take our chart or the plotting sheet, we put our working latitude, that is 37 degrees. We have 12 degrees and 43, 12 degrees and 43 minutes east. That is our assumed position or working position, depending on how you want to be naming it. Hang on, this is wrong here. Azimuth 115. Then from here you draw the azimuth to the moon. This is the moon. This is the direction. And then we are closer to the moon than this. We are closer with somewhere here. How far? 25 miles. So you measure 25 miles from there to there. This is where the position line needs to be. This is not our position. This is our position line. And this you do in a real chart, of course. So that's the moon. How did you like it? Well, a bit complicated, isn't it? But at least we've done it. Let's get a bonus little lecture and thoughts about the moon, because I like it so much. So we have apples and oranges. Don't mix them up. So this is the sun. Place it here. This is the earth. And then we need a moon. So we have a moon here. That's my moon. So what we do with that is that we place them. This is for all the interested people. This is not to scale, right? Sun shines there. We don't need an equator because we're looking from the North Pole. This is the North Pole, but we need a meridian. So this apple thing here, that is pointing towards the meridian. So this is the meridian. So now we have the meridian passage of the sun. And as you can remember, we have here the Greenwich hour angles going westbound all the way over to the meridian again, to Greenwich. This is Greenwich. So we can say that this is now pointing towards the sun, never mind the moon. It's pointing towards the sun, so we have a Greenwich hour angle of 0. And then the earth actually turns this way because the sun sets, it seems as if it's going westbound if you look from above. So the Greenwich hour angle is now increasing. So now we have this Greenwich hour angle, and then it turns, and then we have a Greenwich hour angle of 180 degrees because the sun is over there, and it comes back like this. So, but we have the moon. So the moon, if we place it here, for instance, the sun shines onto the earth and the sun shines onto the moon. So this half is now day on the earth, this half is night, and this also needs, that's maybe important, so we have to do, excuse me, euro sign. Hope I can still put it in a machine somewhere. There we go. So this symbolizes that the sun is shining on this side, so we see half moon. So half moon we would see when the earth is turning like this. So now the sun disappears behind the horizon, so we have sunset. So the sun, here I am at the meridian. Maybe I should symbolize myself also, so because I can be anywhere. Well, this is where I am now. So I'm standing there in England, in London somewhere. So I'm looking up to the moon. So the moon is now at its highest point, so you can see it nicely above in the sky while the sun sets. And then at midnight, this is midnight. Midnight, we can't see the sun at all because on the other side, because it's midnight. And the moon, the half moon is just setting. And here in the early morning, the sun rises. The sun is now in Greenwich hour angle of 270. And then it rises. Here we can't see the moon at all, and here is noon. While we have turned one turn like this, the moon has continued a bit further. And it takes 28 28 days for the moon to go one circle around the Earth. So it has moved on 1/28th of a turn. So 1/28 is approximately 1/24th, so that's about an hour later. So we see the moon now an hour later, and then when it has come here, it has gone 1 week later. That means we have to turn here 7 times, and then we can see the moon during in the middle of the night. So now we have full moon, as you can see, and we stand here and see the moon at the highest of its in the sky, when we don't see the sun at all because of the midnight. And then we turn one more turn here, and then it goes on like this. So you see the point. Why am I doing all this? Well, I want to find out when it is best to shoot the moon. So when it's new moon, that means that we only see the black side of the moon. That means not at all. And the moon is in front of the sun, so we couldn't shoot them anyway because you couldn't see the moon because it's in the way with the sun. So you would see it on midday here. So that's not a very good way to shoot that. We can see here on, for instance, apparently this is a day where it is new moon. It is, the age is there 01 on its first day. Is here on the 21st, whatever, 21st of July. So this is full moon, a new moon. So we can see at 12 o'clock, any day here, I don't know, let's take this day, 12 o'clock, the Greenwich hour angle of the sun is 0 degree. Well, that makes sense because it's exactly above the meridian. So the 0, so it has a Greenwich hour angle of 0, more or less. But so has the moon, you can see that. The moon also has a Greenwich hour angle there of 0. So when we then go further on, we can see, we go and see here. Oops, sorry. So there we are now. So we are on day 7. It takes about a week. So we have got, no, that is not that. This one, the moon has gone on there. So we see the half moon. And we can now see that at 12 o'clock, the sun is still standing, going over the meridian in Greenwich. That makes sense. And the moon has a Greenwich hour angle of some 270 degrees. Well, who would be surprised? This is 0 degrees Greenwich hour angle, 90, 180, 270. So now we continue until we get full moon. Here is full moon on this day. Full moon is here. It is 14 days old, the moon, approximately. You can see 100% of it. And it's on this day here, 1st, 2nd, 3rd of August. And we can look at what happens at 12 o'clock. Well, at 12 o'clock, the sun obviously has its meridian passage over Greenwich, as always. But the moon has a Greenwich hour angle of about, you can see that, about 180, because the moon is over there. So when do we want to shoot the moon? I said that over here it's not good because you don't see it. Obviously you don't have a good enough angle to get a precise fix. But how about here? So if it is just waxing here and it's growing, and then you could just, when you are approximately here, because that's going towards evening, so that is sunset. So so we can do just sunset here. And then we can take at sunset, you know, we have the twilight, so it's perfect to shoot stars. So we can have evening star shot here and using the moon as well. So on day 1 to 3 here, we can have the moon shooting just before the evening stars disappear, or before they appear. Actually, we can shoot it first and then we can continue. This is when we shoot it, the moon, and then we can wait a little bit here. Now the evening stars appear. So when we have a half moon like this, well, when would you want to shoot it then? This is midday, remember? So how about this? In the nice afternoon, So mid-afternoon, you would see the sun here. It has passed the Greenwich hour angle. The sun has a Greenwich hour angle of maybe 45 degrees here. So it's in the afternoon. And the moon is up here, so you can shoot this as well. So here in mid-afternoon, when you have half moon waxing, it is perfect to get a fix immediately. So let's move it further here. So when can you see these two bodies here at the same time? Well, not really. This has already gone down here. It's already going down when you have this seeing this. So I would say when it's over here, I would actually disregard from the sun and just shoot the evening stars and shoot the moon at the same time. And how about when we are over there? Well, then it's about the same, but in the morning. So here I would shoot it when you still can see here, for instance, you can still see the moon there nicely, and you can still see the morning stars. The sun is still behind the horizon, as you can see. So this is perfect just before sunrise and after the morning stars fade. And you can combine them with these. So then we have half moon there, outside the playing field here. Half moon there, move sun a bit. So this is perfect to shoot about here, to get in the mid-morning. So the sun has a Greenwich hour angle here of 90, 180, 270, some 300 degrees. It's mid-morning, so you can see the sun and the moon at the same time. So mid-morning you can combine these two for a nice fix directly. Yes, and then let's go here. That is also possible, but it's too close to the sun, so I would maybe do it here when you still see the morning stars, and then maybe you can use that as well and combine it. But there's so many stars and planets at twilight, so I would say half moon during the day. If you see the half moon, it's actually perfect because you can see it here in the morning, and when it's over here you could see it in the mid-afternoon. So that's just an idea of when you see the moon, you can see what you can use it for in celestial navigation. I love this way of presenting also the tidal waters, because then you can really see how the water is standing still and we are moving in high water, low water, high water, low water. But that is back to Yachtmaster offshore stuff. So we don't want to do that. But in the next chapter we will actually go back in the Yachtmaster schedule, namely to talk about variation and deviation and how we can use celestial navigation to deviate our compass. So stay tuned for the next interesting chapter on the compass check.